Hi there. We looked today in class at a technique called UDU substitution, or integration by substitution. And essentially it's the technique we use when we are looking to undo the effects of chain rule. When we are given a function that either is not able to be turned into power rules through different manipulation, or we're given a function that it's inefficient to turn it into power rule through different manipulations. And for this first lesson, we just looked at identifying the u and du components of a particular function. Okay, so the purpose of a UDU substitution is to replace every x part of an integral with a u, and through that process we're going to be simplifying our problem, making it an easier problem to integrate, a power rule problem most times, or a basic trig. Okay? And so when we're looking at this first problem here, x squared root x cubed plus 1 dx, we're looking for a function that we're going to call u, and that function, when we take its derivative, also needs to be located in the problem. Right? The q that you usually want to look for are parentheses, and even if they aren't written there, you could potentially be looking for the unwritten parentheses. Right, and so in this particular problem, our unwritten parentheses are around this x cubed plus 1. And what I mean when I say unwritten parentheses is a function that could be turned into parentheses. For example, I could rewrite this function as x cubed plus 1 to the 1/2. So it could be rewritten with parentheses, right? And so usually that's the function, that x cubed plus 1, whatever's inside the parentheses, that you're going to want to test as your u. Okay. When we learned this in class, I compared it to working a puzzle. The idea being that when you work a puzzle, for example, especially like when you get to the sky, right, there are 2 billion, it feels like, blue pieces that all look exactly the same. And at some point, there comes a time where you just kind of need to pick up a blue piece and try it. And it may or may not work. And if it doesn't work, you don't give up. You don't beat yourself up about it. It's part of the process. If it doesn't work, you just set it aside and you try a different one. Okay, we're going to be doing the same thing here with our UDU. We've picked a puzzle piece. We've looked for the parentheses to start, but this may not be the right u, and we have to be okay with the fact that it might not be. If it doesn't happen to you here at the beginning of 4.5, which is our UDU substitution, it's going to happen at some point. You're going to get a problem, or you're going to not know what the u is initially. You're going to try something and get it wrong, and that needs to be okay. That's just part of the process. Okay? So here's how you figure out whether or not the puzzle piece actually fits, whether or not we've picked the correct u. When I take its derivative, the derivative should allow me to get rid of every other x that's part of my initial function. This x cubed plus 1, I'm going to be able to get rid of with my u. So what I'm hoping in my du is that I'm going to be able to get rid of the x squared and the dx. Okay, and so that's what we're going to be looking for. Does this fit? So the derivative, which is what we're taking here, of u is du, the derivative of x cubed plus 1 is 3x squared dx, because I've taken the derivative of an x. Okay? And sure enough, when I look in my equation here, I have x squared dx. There's x squared dx. Well, what about the 3, you may ask? Coefficients aren't anything to sweat about. If I have a coefficient in my du that's not in my problem, I can divide it away. Or if I have a coefficient in my problem that's not in my du, I could multiply it in. You can manipulate your coefficients. Just make sure you don't manipulate your variables. So this 1/3, I'm allowed to divide over, thus getting my x squared dx. And that's all we looked at in this first lesson here. It's just what's our u, what's our du, identifying those components. Okay, so we're going to work through 2 more here. Number 4, which is secant 2x tangent 2x dx. And again, we're going to be looking for parentheses, which aren't written, but they are there. Our parentheses in this problem are around that 2x. Okay, and so that's what I'm going to try as my u. Okay, and if in fact that is my correct u, because I'm going to be able to get rid of that 2x and that 2x with my u, if that's in fact the correct u, then I should be able to get rid of this dx piece when I take my du. Okay, so we're going to go ahead and take our derivative here. The derivative of 2x is 2 dx. Sure enough, there's my dx. And again, I have an extra coefficient, but that doesn't matter, that extra coefficient. You can manipulate that, you can divide that over. Coefficients are nothing to worry about. Just again, make sure you don't manipulate variables. We can't have any mixed variables used next to x's. We need to get rid of all of the x's. And so this dx is going to be called 1/2 du. Okay. One more here, number 5 I picked because it's potentially a little bit more challenging. We have the integral of tangent squared x, secant squared x dx. And again, you're looking for your parentheses. And with this one, there are actually 2 sets of parentheses. This tangent squared x could be rewritten as tangent x squared. And this secant squared x could also potentially be rewritten as secant x squared. So then you say, okay, well, which one do we try? Well, this is that sky moment of your puzzle, right? Where if you don't know, if you can't initially see it, you have to try something, okay? So I will tell you how I see this problem very shortly, but I want to demonstrate that whole trying process because that's going to happen sometimes where you aren't going to be able to just see it. And so you would try, and so you might pick, say, the secant x to try, which is going to allow you to get rid of that secant x, right? Which means in doing du, you need to be able to get rid of the tangent x dx. Well, the derivative of secant x is secant x tangent x dx. And we run into an issue there because there's your tangent x, your dx, but your secant x has already been replaced. And you could potentially like try to pull out a secant x, but then you're going to have a leftover tangent x, and we can't have any mixed variables. You can't have an x and a u inside the same equation. You have to get rid of every x. And so this one is not going to work. This is like trying a puzzle piece where it doesn't fit, and that's okay. Now I'm going to encourage you, don't erase. There's a technique we're going to learn in a later lesson where there's a way in some problems to continue to manipulate, and so you don't want to erase because then in some problems you end up having to redo that. So just cross off and try a different puzzle piece. And so if we try our tangent x, okay, I'm going to go ahead and cross this off so we don't get that little line confused later on. Okay, we're going to try our tangent x as our u. Then we're hoping our du is going to be able to get rid of that secant x dx. And our du of tangent, our derivative of tangent, is secant squared x dx. And sure enough, we're going to be able to get rid of not only the secant x dx, but also that squared, which comes in handy. It just makes it a simpler problem. Okay. And so like I mentioned in the beginning, I was going to tell you how I kind of initially see it without just trying something. Anytime I see trigs in my integrals, I'm immediately running through in my head all of my trig derivatives. Derivative of cosine, derivative of sine, derivative of tangent, cotangent, cosecant, secant. And I'm dissecting the problem looking for the derivative first, which I know sounds backwards because with our u du substitution, you usually start with your u. But with trigs, it sometimes is handy if you look for derivatives to see if anything stands out there. And I see here secant squared x, and I know that's a derivative. Secant squared x is the derivative of tangent. And so as soon as I clue in, like, oh, there's a derivative, I'm going to be looking to see, was its antiderivative, was the original function also in the problem? In this case it is. There's that tangent x, derivative of tangent is secant squared. And so I'm going to try that tangent x as my u first, as my first puzzle piece, because I already know it's du, I already know tangent x's derivative is in the problem, which is what we're looking for in the u du. We're looking for a function and its derivative, and so it's already there. And so I would try that first, just because I already see the derivative, and so I'm thinking, you know, there's a good chance that's gonna stick. It's similar to looking through all the blue sky puzzle pieces, and you know there's a cloud, and you see a little piece of white on one of the pieces. You're probably going to try that one first, rather than the one that's all blue, because you know there's supposed to be a cloud there, right? And similar to that, I know there's supposed to be a derivative. I know there's supposed to be a du in these problems. So with the trigs, if I see the derivative, I'm going to try the other one first, just to see if that will allow me to have a u du successfully. Okay? And that's 4.5a.